In this video, we're going to be taking a look at exponents, a basic introduction to the laws governing exponents, and then in a subsequent video, we'll do some examples. Let's begin with the basic concept of an exponent. If I have, say, 2 to the power of 3, we refer to 2 in this case as the base, and the number 3, this little power up here in the top right hand corner, is the exponent. So when we're dealing with exponents, we're dealing with numbers or entities raised to a certain power. 2 to the power of 3 means that we're multiplying 2 times 2 times 2. Use a dot for multiplication in these videos. Similarly, 5 to the power of 3 then would be 5 multiplied by itself 3 times. We can also do this with algebraic expressions. So x to the power of 4 would be x multiplied by x multiplied by x multiplied by x. And of course, combinations of algebraic expressions. Let's say, for example, a plus b to the power of 2. Now, don't make the mistake of saying a squared plus b squared. The bracket itself is being squared, so that is the thing which we must multiply by itself. And when we do this, we must multiply each term by the other terms in the other bracket. So a times a squared, a times b, another b times a, so plus 2ab plus b squared. Now it can be useful to understand what an exponent function looks like graphically. Let's suppose we have the simple function y is equal to 2 to the power of x. If we plot that on these axes, so this is the x-axis, this is the y-axis. If we feed in x equals 1, then y will be equal to 2 to the power of 1, which is 2. When x equals 2, 2 to the power of 2 means 2 times 2, so then we will have 4. And when x equals 3, y will equal 2 to the power of 3. Now, what happens at x equals 0? We have y is equal to 2 to the power of 0. 2 to the power of 0 is 1. In fact, anything to the power of 0 is 1. That may be a little bit counterintuitive. People tend to think that anything to the power of 0 would be 0, but in fact, anything to the power of 0 is 1. So all of the exponential functions pass through the point 0, 1. And what happens out the other side here as we move to minus 1? Y equals 2 to the minus 1. When you have a negative exponent, it has the effect of turning a fraction upside down. So if you imagine that this 2 is actually 2 divided by 1, then if we turn that fraction upside down and change the power to a positive, we get y is equal to 1/2 to the power of 1. Anything to the power of 1 is just the thing itself. So 2 to the minus 1 is actually 1/2. You can see now the shape of the exponential curve starting to appear. What about y equals 2 to the minus 2? Well, we do the same thing again. Write the base as if it were a fraction. And then to get rid of the negative exponent, we're going to turn that fraction upside down and change it to a positive exponent. So we end up with 1/2 squared, which means 1/2 times 1/2. If we multiply the top, we get 1, and we multiply the bottom, we get 4. So I think you can probably see now what's happening. This exponential curve is going to get closer and closer to the x-axis, but it's never going to quite get there. If you imagine out here, let's say we had negative 100. I know that's not to scale, but what would the y value be here? Y equals 2 to the negative 100. That is the same as 1/2 to the power of 100, which is going to be 1 multiplied by itself 100 times, divided by 2 multiplied by itself 100 times. And obviously this denominator is a very large number, and so this is going to be getting closer and closer to 0. So our curve is going to look something like this. Now what happens if we change the base? Let's suppose we're looking at y is equal to 3 to the x instead of 2 to the x. Then when x is 1, y will be 3. When x is 2, y will be 9. 2, 4, 6, 8, 9, way up here. But 3 to the 0 is still going to be 1. So we're going to pass through this same point. And now what's going to happen on the other side is that the function will get closer and closer to the x-axis again, but it'll do it more quickly because of the larger denominator. So we can kind of imagine that it looks something like. So it's good to have a visual of what an exponential function looks like as we move forward with these laws of exponents, particularly the fact that all of these exponential functions pass through the point 0, 1. Okay, let's look at some of the laws now. Let's start with the multiplication law for exponents. And let's start with a numerical example just to make it clear what's going on. So if we have 2 to the power of 2 multiplied by 2 to the power of 3, we can expand that out. 2 to the power of 2 means 2 times 2 for the first term, and then we're going to multiply that by 2 to the power of 3. And what we have here is 2 multiplied by itself, total of 5 times. So I think you can probably see that the exponents on these two terms add up to the exponent in the answer. So if you have some base, remember this can be anything, we'll just call it a for now, and it's raised to some power, we'll call it m, and we're multiplying by something else which has the same base, must have the same base to be able to do this, and it's raised to the power of n, then the answer is simply a to the power of m plus n. That's our multiplication rule for exponents. Division is very similar. Let's Let's imagine again a specific example, 2 to the power of 3 divided by 2 to the power of 2. If we write this out explicitly, 2 times 2 times 2 divided by 2 times 2. We can cancel all of these 2's with each other, and we're just left with a single 2, or 2 to the power of 1. And now notice that if I take the exponent in the numerator and I subtract the exponent in the denominator, I get the exponent in the answer. And that is basically the division law for exponents. Algebraically, some base to the power of m divided by that same base to the power of n is equal to a to the power of m minus n. And there you have the first two rules for exponents. Let's now move on to the power rule. For exponents. Again, with a numerical example, just to see what's happening, 2 squared, all raised to the power of 3. What does this mean? Well, this means I've got 2 times 2 multiplied by itself 3 times, multiplied by 2 times 2. So that's 2 times 2 times 2 times 2 times 2 times 2. 2 multiplied by itself 6 times, so that's 2 to the power of 6. And what you notice here is that the exponent inside the bracket multiplied by the exponent outside the bracket gives me the exponent in the answer. And this is our power rule for exponents, so we can write this as a to the m raised to the power of n is simply equal to a to the power of m times n. Okay, next rule. Let's now look at how we distribute exponents. Say, for example, we have 2 multiplied by 3, and we're looking to square that. So when we square something, we multiply it by itself. So let's just leave what's in the bracket alone for a second. Now, when we multiply things together, we can put them in any order we like. So 2 times 3 times 2 times 3 is the same as 2 times 2 times 3 times 3. We can group things together without changing the value of the answer. And we're left here with 2 times 2 is 2 squared multiplied by 3 times 3, which is 3 squared. So you'll notice what has happened here is that the exponent has distributed itself to each of the terms inside the bracket. And we can do that when what's inside the bracket is either a multiplication or a division. Let's look quickly at a division, just to show you what I mean. If this was 2 divided by 3, all squared, that means 2 divided by 3 multiplied by itself. When we multiply fractions, we multiply the top, 2 times 2, and we multiply the bottom, 3 times 3. And you can see that we've ended up with 2 squared divided by 3 squared. So again, the exponent outside the bracket gets distributed to the things inside the bracket because we are, in this case, dividing. So let's just write that algebraically. We've got, for multiplication, we've got a multiplied by b, all raised to the power of m, is the same as a to the m, b to the m. And a divided by b to the power of m is equal to a to the m divided by b to the m. It's important to recognize that this only applies when we are multiplying or dividing in the bracket. Don't make the mistake of distributing an exponent when you have pluses and minuses inside the bracket. In those cases, we need to multiply out fully and apply the concepts of FOIL to expand brackets with all of their terms. So let's just clarify that last point for you. We often see students make the mistake of writing something like a squared plus b squared is equal to a squared plus b squared. They take the exponent and they distribute it to 2 terms in the bracket, which are either added or subtracted. And this is simply not true. We know that if we apply the exponent correctly, when we're squaring something, that means multiply it by itself. So we must include all of the terms in the brackets. And when we multiply brackets together, we have to apply the FOIL principle. So we get a squared plus ab plus ba plus b squared, which is a squared plus 2ab plus b squared. And it's this middle term that gets missed if you don't expand this expression correctly. So be very careful when you have exponents applied to expressions that have pluses and minuses. So a quick numerical example just to make sure this concept is fully understood. Let's take the simple example that we have 1 plus 2 squared. Now, obviously, because we know everything inside the bracket, we know that the answer here should be 1 plus 2 squared. That's 3 squared, so the correct answer should be 9. Now, let's do it by correctly expanding the bracket. 1 plus 2 squared means 1 plus 2 multiplied by 1 plus 2. So we do 1 times 1 is 1. 1 times 2 is 2. 2 times 1 is 2. And 2 times 2 is 4. So we get the correct answer. 4 plus 2 plus 2 plus 1 is 9. If we made the mistake of just squaring each term, then we would get 1 squared plus 2 squared, which comes out to be 5. And that is clearly wrong. This is the correct answer. This is the correct answer. This shows what happens if you distribute the exponent in the wrong fashion. So be aware of that. Okay. Labored that point enough, I think. Let's move on to more exponent rules. Let's look at negative exponents now. We looked at these briefly when we were graphing the exponential function, so this should not be completely unfamiliar. 2 to the power of -3. Now the way I like to do or deal with the negative exponent is to talk about turning a fraction upside down. Well, here the base is not actually a fraction, it's a whole number, but we can write it as a fraction just to keep the rule consistent. So let's write the base as a fraction, 2 divided by 1 to the power of -3. The negative exponent means turn the fraction upside down and change the exponent to positive. Now I have 1/2 to the power of 3, so that's 1/2 times 1/2 times 1/2 times 1/2, or 1 divided by 2 to the power of 3. Applying the exponent to the top and to the bottom of this fraction, which is just 1/8. So algebraically, we can write that a to the minus m is equal to 1 divided by a to the m. So when we have a whole number for the base, we can use that expression. More generically, you can use, if you have a fraction in the base raised to a negative power, you're going to turn that fraction upside down and turn the exponent into a positive. So that's how we deal with negative exponents. Again, in the next video, we'll go through lots of examples of these. So if it's a bit bewildering at the moment, practice will definitely help. Now we'll move on to rule number 6. Okay, rule number 6, we're dealing with fractional exponents. So this is not fractions in the base, but fractions in the actual exponent itself. Now you may be familiar with the idea that 2 to the power of 1/2 is the square root of 2. We don't normally write a little 2 here for the square root because the radical sign default is square root, but just for clarity in this rule, I'll put it there. And what you should notice is that the denominator of the fractional exponent becomes the factor here on the radical. So by similarity, if I wanted 2 to the power of 1/3, that would be equal to the third root of 2. Again, the denominator becomes the coefficient on the radical here. So we can write this generically that some base to the power of 1/m is equal to the mth root of that base. Let's now look at a slightly more complicated example. Now we've said that a to the power of 1/m is the mth root of a, and we also know that from the power rule that a to the power of m all raised to the power of n is a to the m times n. What we're going to do here is combine those two into a rule when you have something like this, a to the m divided by m. What do you do there? Well, you can use the second of the rules above to break that down into a to the 1 divided by m, all to the power of n. And now we can apply the first rule above. A to the power of 1 over m means the mth root of a, and that whole thing is raised to the power of n. So what happened? The denominator of the fraction became the coefficient of the radical, and the numerator became the exponent outside the bracket. Now we could have done that slightly differently. We could have pulled out the 1 over m and left the n inside. So this is exactly the same, because again, if I multiply these two exponents together, I get n divided by m. And so this becomes now a to the power of n, and then I'm taking the mth root of that expression. And these two are exactly equal to each other. You can do the expansion either way. And what we're normally looking for is which one gives us the easiest to calculate answer. For example, let's just do a quick example. 8 to the power of 2 over 3. We could either write this as the third root of 8 all squared, or we could write it as the third root of 8 squared. Now, if you had this problem to deal with, the third root of 8 is 2. 2 times 2 times 2 is 8. So this first expression simplifies to 2 squared, which is 4. So that particular format works nicely for this problem. On the other hand, if you use the second expression, you would get the third root of 8 times 8 is 64. And depending on how good your maths is, you may know that the cube root of 64 is 4, or you may not. But both give the same answer. That's the important thing. You can deal with the problem in either way, get the same answer. Okay, now let's combine fractions and negatives just to deal with the most complicated situation. So here we go, number 7, fractions and negatives. Now we've dealt with each of these individually. Now we're simply going to combine those together. And it might be best again to start with a simple example. 8 to the power of negative 2 over 3. So, keeping our mind focused, first of all, let's get rid of that negative exponent. So we know how to do that. We are simply going to turn the fraction inside the bracket upside down to make it 1 over 8. And now the exponent outside becomes positive. Now we use our rules for fractional exponents, so we know that this is the same as 1 divided by 8 to the power of 1/3 all squared. So that is the cube root of 1 over 8 all squared. Cube root of 1 over 8 is 1 over 2, so that's 1 over 2 all squared, and that is equal to 1 divided by 4. So you convert the negative to a positive exponent by turning the fraction upside down inside the bracket. and then break that fractional exponent into its two pieces to give you the radical and the power. And so generically, we could write that as a over b to the power of negative m over n is the same as b over a to the positive m over n, which is the same as b to the m over n divided by a to the n over n, which is the nth root of b to the power m divided by the nth root of a to the power m. Again, we'll do lots of examples in the next video, so don't worry if that seems a bit bewildering. We will definitely come back to it. The final rule, and it's just one you have to remember, is that anything to the power of 0 is 1. We showed that graphically at the start of this video. So 2 to the power of 0 is the same as 1/2 to the power of 0 is the same as pi to the power of 0, same as 15 to the power of 0. They're all equal to 1. X to the 0 is the same as y to the 0 is the same as x divided by y to the 0. It doesn't matter what it is, it's still 1. Anything to the power of 0 is 1. X cubed, y squared plus 3 pi plus sine theta, all to the power of 0 is 1. Don't forget that. Okay, that concludes this video, and in the next one we will do lots of examples. If this has been helpful, please like and subscribe, and then you'll receive notification of when new videos are posted. Thank you very much.